This is Porterville College, Physics 104B, Chapter 25 homework, starting with number 16. The EMF of the battery, it delivers 27 joules of energy as it moves 3 coulombs. So EMF is a measure of joules per coulomb, which is volts. So 27 joules divided by 3 coulombs is 9 volts. Number 19, 2 resistors in parallel, and then that pair is in series with a third resistor. What's the combination? So we'll collapse the 2 that are in parallel, come up with an equivalent resistance. So over to the right, you see resistance parallel equals the reciprocal of 47 kiloohms plus the reciprocal of 39 kiloohms, and then the reciprocal of that sum, and we get 21.31 kiloohms. Then we take that 21.31 kiloohms, put it in series with the 22 kiloohms, so we add those together and get 43 kiloohms total. Number 20, what resistance do we need to get a total of 45 kiloohms in parallel? So the way resistances add, their reciprocals add, so the total, 1 over 45 kiloohms equals 1 over 56 kiloohms plus 1 over R. Subtract 1 over 56, and that's going to be 1 over R, so then take the reciprocal of this, and you should get 229 kiloohms. Number 23, what's the battery's internal resistance? We're going to apply Ohm's law to the battery. So current equals the EMF divided by the internal resistance. So internal resistance is EMF divided by current. 9 volts divided by 0.2 amperes, and we get 45 ohms. I take it to one significant figure, so 50. Number 24, all the possible combinations to have a 1, 2, and 3 ohm resistor. So I start with all 3 in series, and you just add them up, 1 plus 2 plus 3, that gives 6 ohms. You can have all 3 in parallel, and that's the reciprocals, 1 over 1 plus 1 over 2 plus 1 over 3, then the reciprocal of that, 0.545 ohms. You can have 1 in series with a parallel combination of the other 2. So what I've done, here's the diagram, and what I've done first is said, okay, here's the 1 ohm and then the 2 and the 3, and I've added them. Then the next line I've done the 2 and then 1 and 3, and then the 3 with the 1 and 2. So you can see what I've done, the series and parallel combinations. So you should get 2.2 ohms, 2.75 ohms, and 3.67 ohms. Another possibility, let's scoot this up, is to have a parallel combination of 2 that are in series with another one. So what I've done in these lines is put the 1 on top and 2 and 3 on the bottom, then the 2 on top, and then the 3 on top. So, for example, with the 1 on top, you're first take the bottom part. The 2 and 3 are in series, so that's a 5 ohm series combination. So this will be 5 to the negative 1 plus 1 to the negative 1. Take the reciprocal of that, and you get 0.83 ohms. The other combinations give 1.33 ohms and 1.5 ohms. Number 25. Note how I've designated the currents. I've drawn I1 going around here on the left loop, I3 going up the center, and I2 going counterclockwise around the right loop. So I apply Kirchhoff's three laws. First, the node law, and I'm applying it to this point right here, that I1 is going in, I2 and I3 are coming out, so I1 minus I2 minus I3 equals 0. For the left loop, I'm going to go with the current, so plus E1 minus I1 R1 minus I3 R3, and back around again, equals 0. When I clean that up, to be able to put in matrix form, I get I1 R1 plus I3 R3 equals E1. For the right loop, I start with E2, and I'll go I'm going to go clockwise, so first E2, and then I'm going against the current. I'm going upstream, so that's going to be plus I2 R2. Take it around. Now I'm going with the current, so minus I3 R3 equals 0. And I cleaned it up for matrix form. I2 R2 minus I3 R3 equals negative E2. So now I'm going to make substitutions with the resistor values and the electromotive force values. And so I've got this system of linear equations, and below it is the system in matrix form. And now I'm going to solve that matrix. The first thing I'll do is, in order to get this one turn it into a 0, I'll take twice the first row minus the second row and put that difference in as the second row. So the second row becomes 0, negative 2, negative 3, 6, or negative 6. Then I want to make this 4. I want to turn that into a 0. So if I take 2 times the second row and add it to the third row, and then make that that sum be the third row, I'll get for the third row 0, 0, negative 7, negative 13. Then I solve each of these equations for these rows, starting with the bottom one. This bottom row says negative 7 I3 equals negative 13. So we solve for I3 and get 1.86. Then I work my way up through the rows. So up through the second row, now that I know what I3 is, I can plug in for the equation of the second row, and I get I2 is 0.214 amperes. And then plug into the first row, and I get I1 is 2.07 amperes. For number 32, we're doing rough estimates, order of magnitude estimates, just to get a feel for, given the order of magnitude of the capacitor and the order of magnitude of the resistor, what kind of time frame are we talking about for the time constant? So for part A, we've got microfarad, so 10 to the negative 6 farads times an ohm, and that gives 10 to the negative 6 seconds. So we're looking at a time frame in the microseconds. For part B, we've got our microfarad times 10 to the third ohms. So that comes out to 10 to the negative 3 seconds. So we're looking in the millisecond range. For the last one, 10 to the negative 6 farads times 10 to the 6 ohms, we get 1 second. So we're looking in the second range. Number 34. We're looking to solve for the time for the capacitor that uncharged. Okay, so 250 volts is applied to the combination. How long does it take the capacitor voltage to reach 200 volts, so it's charging. So we have all this given information that I have written up here. We have our equation for voltage as a relation to time. So I'll solve this equation doing a few lines of algebra, and I get down here that time equals negative RC times natural log of 1 minus VC over E. And when we plug in the given information, we get 7.56 seconds. And by the way, I just have off to the side that the time constant equals RC, which is 4.7 seconds. Number 37. The book says take each resistor to be 1 kiloohm. I misread that as 1 ohm, and I just decided to continue on like that, so I've made that the assignment. Just do it for 1 ohm. If you're interested in looking at this problem, what would the answer be if we used 1 kiloohms? I encourage you to go through and do it again, and you'll see an answer that relates to the answer that we're going to get. But we're going to take this assignment as taking each of those resistors as being 1 ohm. So what we can recognize is, before I continue, I'm going to show 2 solutions to this problem. The first solution, the one on this page, is collapsing the combinations of resistors down to 1 equivalent resistance. Then after I've solved it, I'm going to go back and solve it again using Kirchhoff's laws, just to show that you can use either way to solve these problems. So here is collapsing the combinations of resistors. We recognize that these two that are at the angles, they're in series with each other. And that series is 1 ohm plus 1 ohm, that's 2 ohms. Now this 2 ohms and this 1 ohm, they're in parallel with each other. We do the parallel resistor equation, 1 over 1 plus 1 over 2, take the reciprocal of that, and we get that this parallel combination that I've circled here in blue has an equivalent resistance of 2/3 ohms. Now it's become a series of 1 ohm, 2/3 ohm, and 1 ohm. So the total resistance for the entire circuit is 1 plus 1 plus 2/3, or 8/3 ohm. So this circuit can be thought of as the EMF with 1 resistor that is 8/3 of an ohm. So we can find the current, the total current, and that's the EMF, which is 6 volts, divided by the total resistance, 8/3 of an ohm. And so we get a total current of 9/4 amperes. Now, we want to find the voltage across the vertical resistor. So let's go back and look at the parallel combination that vertical resistor is a part of. That vertical resistor is in parallel. I'm going to bring this down just to look at the diagram again. The vertical resistor is in parallel with this 2 ohm combination. In parallel means they're at the same voltage, they have the same voltage drop. So let's go back up and down. The parallel voltage, which is the voltage across the parallel combination, is the total current times the parallel resistance. So 9/4 ampere times 2/3 ohms is 3/2 of a volt. And that's equal to the voltage across just the vertical resistor. So we can apply Ohm's law to the vertical resistor. We can say the current is equal to the voltage across the vertical resistor divided by its resistance. So 3/2 of a volt divided by 1 ohm, and we get an answer of 1.5 amperes. I'll solve the same problem, number 37, using 1 ohm for each of those resistors, using Kirchhoff's laws. So I've designated I1 going around the left loop, called clockwise, I3 going straight down the vertical resistor, and I2 going clockwise around the triangular loop. At node A, which is right where my pen is pointing, we can say I1 minus I2 minus I3 equals 0. The left loop, going clockwise, we have E, later I'll replace that as 6 volts, but now I just call it E, minus I1 minus I3 minus I1 and background equals 0. So when we clean that up, we get 2I1 plus I3 equals 6. Next we apply the right loop. The right loop is, I'm going to go back, bring the picture down. The right loop, we start at node A and say negative I2 minus I2. Then we're going against the current, so plus I3 equals 0. And so when we clean that up for the right loop, we get negative 2I2 plus I3 equals 0. So I take those three equations, put them in matrix form. Here's the matrix right here. 1, negative 1, negative 1, 0, 2, 0, 1, 6, and 0, negative 2, 1, 0. And then I want to get my zeros in the lower left-hand corner. So I can take twice the first row. I want to turn this 2 into a 0. So I want to take twice the first row, subtract the second row, and replace that in with the second row. So then the second row becomes 0, negative 2, negative 3, negative 6. Then I want to turn this negative 2 into a 0. So I'll just take the second row, subtract the third row, so we get 0, 0, negative 4, negative 6. We're only interested for this problem in the current across the third, or what the third current is. The current across the third resistor, which in my picture is current number 3. So negative 4I3 equals negative 6, and that becomes 1.5 amperes. Okay, so I misspoke a minute ago. This isn't the third resistor, it's just the current we're looking for is this I3. That's what I meant to say. So 1.5 amperes. Number 46. For number 46, find the current supplied by the battery and the current through the 6 ohm resistor. So the current through, this resistor. So we can recognize that the 2, the 4, and the 6 are all in parallel with each other. And when you do the parallel equation, you get resistance parallel equals 12/11 ohms. So the entire resistance of the circuit is the 1 ohm plus the 12/11 ohms, and that gives us 2.09 ohms. So then we can say the current through the the total current is the EMF of 6 volts divided by the total equivalent resistance, 2.09 ohms, and we get 2.87 amperes. Now, we want to find the voltage just across the 6 ohm resistor. We recognize that the voltage across the parallel combination, which is everything here, is equal to what the EMF supplied minus the voltage drop across the 1 ohm resistor. So after the 1 ohm resistor, whatever's left goes across the parallel combination. And all the resistors in the parallel combination are at the same voltage. So we get the voltage across the parallel combination is EMF minus I total times 1 ohm, which is 6 volts minus 2.87 volts. So the voltage across the parallel combination is 3.13 volts. And so now we apply that and we say that voltage is across the 6 ohm resistor. So its current equals voltage divided by resistance. 0.52 amperes. Number 57. We're looking at a capacitor charged at 5 joules initially, then discharged across a resistor to only 2 joules. I'm sorry, it loses 2 joules, so it discharges to only carry 3 joules. So here's the formula for energy held in a capacitor, 1/2 CV squared. So I've set this up as a ratio, final energy divided by initial energy. That's going to be 3 joules over 5 joules. Equals 1/2 CV squared over 1/2 CV naught squared. The 1/2s and the C's divide out. And we're left with 3/5 equals V over V naught squared. Now I'm going to plug in the numerator, because V is V naught times e to the negative t over RC. And we've still got that squared up there. Now the V naughts divide out, and we're left with 3/5 equals e to the negative 2 over RC. And I've turned this into a logarithmic equation. So the natural log of 3/5 equals negative 2t over RC. We solve for C. C is negative 2t divided by R, natural log of 3/5. Plug in T, plug in R, and I get capacitance is 3.37 microfarads. Number 71. This involves looking at data that's on a chart. And so the first thing it asks is, what is the battery voltage? Well, the capacitor is going to charge up and asymptotically approach the battery voltage so that within close to about 5 time constants, it's going to be within 99% of that voltage. You can look at the chart and see that it's approaching 9 volts, and so that's the battery voltage, 9 volts. Now it says, for part B, what is the time constant? So we can use this equation, V equals E times 1 minus E to the negative T over RC. And we're going to pull data off the chart, V, the EMF, and T, and we're going to find RC from that. Now, I've already done this solution in number 34. Number 34, where I've solved for RC equals negative T over natural log 1 minus V over EMF. So when we know T, we know voltage, we can solve for this. So I've picked data points off the chart. You pick whatever data points, easy points that you can see. I found 2 of them. The first one I found was voltage is 7 volts, and as I look at the chart, it looks like that's happening at a time of 2.4 milliseconds. So when I plug those data values into the equation, I get a time constant of 1.6 milliseconds. Then I check with another data point. So another one that was easy to see was at 5 milliseconds, voltage was 8.6 volts. When I plug those in, I also get 1.6 milliseconds. So that confirms for me nicely that 1.6 milliseconds is roughly the time constant. And then we want to find capacitance. Capacitance is time constant over R, because that's RC over R. So I'm using a time constant of 1.6 times 10 to the negative 3 seconds. Divide by 4,700 ohms, and I get 3.4 times 10 to the negative 7 farads, or 340 nanofarads.